So we have this typical question that is used to analyze shear stress, shear strain, and shear modulus, and I'm going to walk you through step by step on how to do those calculations, as well as identify common mistakes that tend to happen. Now, the first thing I would want to bring your attention to is what we have here is this force, and it's perpendicular to this face that I'm highlighting. Now, the reason why that is quite pertinent information is because if you use the wrong face to find the area of this shape, then you're going to end up getting either the wrong stress that you're trying to find or the wrong strain, or everything could just go wrong. So let's start by finding the shear stress though. So if we were to find the shear stress, we would use this formula that says shear stress equals force divided by area. And of course we need to find out what our area is, and to do that we have to identify which of these faces our force is parallel to, because we're finding shear area. So it will be this face here that I'm highlighting in yellow that we take into consideration, because if we were to use that face highlighted in purple, then instead of getting the shear stress, what would end up getting is actually direct stress. So that's something to be mindful of. So now with the correct face in yellow, we're going to use the force that we get, and that force is 50 kilonewtons, so 50 multiplied by 10 to the power of 3. And then because we're using that area highlighted in yellow, our length is 150 millimeters, but I'm going to convert that into meters, so we get 0.015, and that's what we're going to multiply now by 0.075. So now that's going to give us a sheared area of 44.44 megapascal. So this here is representing our shear area. And now for the shear strain, this is another area that tends to be very evasive for some people, so I'm going to break that down for you to understand fully. Now, once again, with the shear strain, it's very important for you to differentiate shear strain versus direct strain. For shear strain, if you can look right here where I'm circling that slanted length, that's the side, or that's the depth that's being distorted. And what we had here is the 60 millimeters highlighted right there, and because of the force applied, it then distorted that depth by 0.3 millimeters. So what would happen now is, for the shear strain, we are to use the change in length divided by our initial length. And in this instance, the initial length that we're focusing on is the 60 millimeters, and that 0.3 that we have there is representing our change in length. So what we would end up doing here now is to divide our change in length, which is our 0.3, by the initial length that we have, which is our 60. And that's going to give us a strain of 5 times 10 to the power of negative 3, or 0.005. And strain is dimensionless. If you notice here, I did not change the units, and that's because it doesn't really matter for strain. So that leaves us now with the shear modulus. So let's go ahead and calculate our shear modulus. Now for the shear modulus, or our modulus of rigidity, we're doing a measure of the stress that we have divided by the strain that we just calculated, and our stress was 4.44 megapascal, so times 10 to the power of 6, and our strain here is 5 times 10 to the power of negative 3, and that leaves us with 888 megapascals. If you'd like to learn how to apply this concept to sheared bolts, then you should check this next video out, where we go in depth on applying this even more further.